Hello and welcome to PyData Global 2024. You are in Build Your Own Transformer. Welcome, everybody. Thank you to our speakers for your time and energy and being here with us today. Attendees, this is a 90-minute tutorial, so lots of time for you to take advantage of interacting with your speakers and with the community. So please feel free to use your chat feature. That should be on the right side of your screen. And then right underneath that is the Q&A. So towards the end, and maybe even throughout, if they want to accept some questions, there is an option for you to type in that question, and the speakers will be able to see that and help get those questions answered for you. So please chat away, interact, enjoy. Thank you all so much for being here, and the floor is all yours.
Thank you, Tamara. Hello, everyone. Let me share my screen first. Okay, hello, everyone. Welcome to Build Your Own Transformer workshop. My name is Chuxing Liu, and I'm also excited to introduce my two other speakers, Shito and Shefali. Today, we are going to dive into transformers and guide you through building self-attention step by step using only Python and NumPy. Before we dive in, a quick check. If you are here for Build Your Transformer workshop, you're in the right room. And feel free to tell us where in the world that you are dialing from. New Orleans, nice. Early bird. Atlanta. Okay, many East Coast folks. Okay, and lots of Europeans. Wow, we really have a lot of people from different places from the world. That's nice. I don't see anyone from the west coast of USA, which might be too early for them to get up. Okay, so I guess good morning, good afternoon, and good evening for many of you. Let's get started. Before we dive in, actually, here's our plan for today. We'll start with a 10-minute introduction to transformers. And then after that, we'll spend the majority of our time today working on a Google Colab notebook. You will be using a Google Colab, and so hopefully you can use a Google account and have access to Google Colab. And if you don't, please let us know. We can email you a copy of the Jupyter Notebook as well. Okay, so let's get started. A little overview and history of, a little bit overview and history of the natural language processing. So over the last decades, we've seen a significant evolution. We started an era before machine learning, and then we moved to word embeddings. And then came the era of the deep learning that came the RNNs and LSTMs, which were the state of the art before Transformer was born. RNN, or recurrent neural network, they process sentence sequentially, step by step using hidden states. However, RNN struggles with vanishing gradients when the sequence gets long. So then it came LSTM, or Long Short-Term Memory Network. LSTM is also another type of RNN. It processes the sequence sequentially, but it has long short memory, so it solved the problem of the gradients. However, it's still sequential processing. They struggle with long sentences, and they struggle with the problem of scalability. So that brings us to Transformer. It is introduced in 2017. It has revolutionized the field by laying the groundwork for all the large language models that came afterwards. The current landscape of the large language models, it lays the foundation for all these popular apps that we're using today, ChatGPT, Claude, or Gemini. We also have popular open source models like Llama from Meta. And it's also worth noting that some of the image processing models, image generation models, are also using transformers. Um, that this is why learning about transformer is so important. Understanding them help us grasp the foundation of these AI models and improve our coding and debugging skills when using them. Now let's break down what transformer is. It is an architecture with two main parts. On the left-hand side is the encoder, and on the right-hand side is the decoder. Each part plays a crucial role in how transformer process information. It usually takes inputs that is large chunks of text. Imagine the whole internet of words. And then it outputs the next token, or it predicts the next word. Starting from the bottom, when we have inputs, let's say a book, the first thing we need to do is to convert it into numbers. So that comes the input embedding and the positional encoding that is on the left bottom side of the slides. An example would be a sentence, "I love learning about transformers." And the first step is tokenization. We want to convert it into each single word. And then we use embedding. It is a vector with a length of 512 numbers. These numbers represents the meaning of each word. The embedding will be trained during the transformers training. And then the third step, we want to also include some information about the positions. So we use positional encoding to add some numbers onto the final vector. Once we have processed our inputs, we will move into the attention part. And I just want to motivate all of you a little bit more about why we want to learn attention. Let's say there is a sentence, the animal didn't cross the street because it was too tired. Here it is tricky for the machine to really understand or figure out what the word "it" refers to, right? Is it the animal, or is it the street? Because there were, or is it tired, right? Self-attention is like magic here, because instead of looking at the sentence sequentially, it look at the sentence as a whole, and it looks at all the relationship between it and all the other words in the sentence. In this example, after the training, we can see that it has different level of strength. as it relates to other words. And the darker color means that the strength is stronger. So in this case, it has a stronger alignment or relations with the animal. Okay, so let's get into our workshop. Here is the link on Google Colab. After you get onto this link, you should do copy to your own drive. You can also find this link in the resources in this chat room or on the schedule. If you have get to this, if you're able to get to the notebook and copy to your own drive, please send a thumbs up emoji, or I think you can thumbs up an emoji, or put it in the chat. That works too. Okay, good. If you want to test if it's working for you, you can do you can add it some on your notebook and see if it works. Or try to run print hello world. If it works, then we can get started. All right, so I'm gonna get started, and if you have any questions, please feel free to ask questions in the Q&A or in the chat. My two other speakers will answer your questions or help you debug. Okay, so let's get started. In this notebook, we'll break down the attention mechanisms as described in the paper step by step using only NumPy. By the end of this walkthrough, you'll have a clear understanding of what is the underlying architecture under attention or under transformer. So please go ahead, first run the libraries. Okay. So now we are at step number 1, create embeddings for words. This part, basically we need to break down our sentence into a set of numbers. Our sentence is "you are amazing," so we have 3 words here. We'll just assume that these 3 words are 3 different tokens. In reality, we might have more. So for simplicity, we also assume that the word embeddings are vectorized in an 8-dimensional space. how to get the cats. It's in the setting and here. Okay. Okay. So we use 8-dimensional numerical representation to describe each words. Here, down here, you can see that this is an example with 7 numbers, let's say. Cat, kitten, dog, horses. They can be represented with each with 7 numbers, and different numbers represents that. Let's say the first number represents whether they are a living being. The second number represents whether it's a feline or not. The third number represent whether it's a human, and then the next is the gender. So all these different words have a certain meaning for this for all these different numbers have a certain meaning for the word. So in this example, we just use number 8, but in the paper, they use 512 dimensions. So that is also how magical our words are. Our words have all these different meanings that represent it. Okay. Here are some more visualization. You can see that in the first graph, cats and kittens are closer in the vector space because they have a similar meaning. In the second visualization, man and woman's and queen and king, we can see that the differences between them are also similar because it represents that the distance between them is the gender. Okay, so that comes to our first exercise. We want to use a function called okay, up here. We want to use a function called mp.random.rand function. Feel free to use ChatGPT for help if you need. But basically, we use this function to generate a vector with random numbers with a length of 8. So your task or what you want to do right now is fill out the parts with the question mark and print and hit run to see if you can print out word embedding shape and an example word embedding for the word amazing. I'll give you 30 seconds or 1 minute. If you are done, send a thumbs up as well. Okay, lots of thumbs up. That's great. Okay, so here comes the answer. Embedding dimension, this is a constant or it's a scalar. In this example, we picked the number 8. And for randomly initialized word embedding of size, we use numpy.random.rand and then number of 8 or embedding dimensions. So these 3 will have the same answers. Okay, and then we hit run. So if you are doing it correctly, your word embedding shape should be 8. It should be a vector. And then the word embedding for amazing should look like this. It's a set of random numbers for now because we haven't trained the model. But after we train the model, the embedding will have meanings. All right, I hope everyone get this right so we can get quicker. How is it that you get the exact same number as me? Because for reproducibility, we set seeds. Yeah. If you delete set seeds and run it again, probably you'll get a different number. Okay. All right. Okay, so next step, we also want to add positional encoding to the vector. Positional embedding encodes the relative position of tokens in a sequence, and that is added to the word embedding for computational efficiency and dimensional consistency. Um, Generally, we just add these numbers onto the word vector instead of having a longer vector. So we still have a vector of 8. It's just we add some more numbers. We change the numbers onto the embedding. In the paper, it uses sine and cosine functions. So I have defined the positional encoding functions for you. And your next task is to add positional encodings to each word embeddings. Fill out here this question mark and see if it works. Again, if you are able to get through this, send a thumbs up. Okay, I saw 2 thumbs up. Okay, 2 more, 3 more. Nice. Okay, so this one, the answer is just to combine the word embeddings and the positional encodings together. That's true. Yes, this one should be amazing. Oops. I should not run this twice. Okay. Okay. Okay, thanks. The reason why we decided that we want to print out amazing is because in the sine function, the first word's position is 0, so it doesn't really encode anything. So we want to print out another word that has a different set of numbers. So as you can see, amazing before encoding, the number is 0.3042 and followed by 7 different numbers. But then after the positional encoding, it's 1.21 followed by another 7 numbers. Okay, so here we are done with step number one. Now we have embeddings for every word. Let's move on to step two. So step two, basically, we just want to stack three vectors into a matrix. And in the paper, this matrix is called capital X. And here you want to use NumPy's function vstack to stack them together. So go ahead and see if you can finish this. Once you're done, send a thumbs up. Okay, so as you can see that if I print out word embeddings, it's a dictionary with each word as its keys and then their array of numbers as their values, right? So what I want to do is just stack the values. So the answer is the list of word embeddings values. And then once you hit once you hit run, you should be able to see that input matrix S has a shape of 3, 8. Sequence length is 3. So we'll talk about sequence length again, but just think about sequence length as the length of the sentence. And in this case, "You are amazing" has 3 words. So sequence length is 3. So we have transformed our sentence in 3 words into a 3 by 8 matrix. All right. Next, let me move over to Sheetal to talk about weights, to talk about Q, K, and V, which is the most magical part of Transformer.
Hi, just give me a minute. Let me share my screen. And we are here. If if there's any issue with my sound, please do write in the chat because my earphone is being quite funky today.
It is a
Okay,
little bit low.
okay. How about now?
Uh,
Hello,
Still a little bit low. It feels like something's blocking.
hello, hello, hello. Um,
Yeah, just go
okay,
ahead. Probably speak louder. Yeah.
okay, okay. Um, so query, key, and value are the most important part of attention, which is what um, makes us understand these relationships between the different words in the sentence, right? So this is the example that Chuksin gave earlier. Um, the sentence is the animal didn't cross the street because it was too tired. Now here, this diagram basically shows us how attention captures the relationship between a word it and tries to figure out that it refers here to the animal, not the street, because these both are nouns and it could refer to either of them, but in this sentence it refers to the animal. Now, how does Transformers understand that or figure that out, right? we are going to break it down and we are going to try to understand what does query, key, and value matrix each mean and what they are even. So, firstly, query, key, and value matrices are just transformations of our input matrix X. In this example, we are going to try to understand from this diagram itself. Query for the word it is essentially trying to ask a question, what does it refer to? So the query matrix is going to be encoding the information that tries to understand what does it refer to. We are going to try to compare the query of word it to the keys of all the remaining words to understand what does it refer to. So what is going to be the key and value of each of these words is going to give us some meaningful information to answer this query. So what is the key of animal? The key of animal is that animal is the subject. It is a living being. It is capable of being tired. So key is just information about this word, right? And then value is the information value about any specific word is what is that word doing in this context or any other useful information about this word that can help us understand whether this word is closely related to the query of another word or not. So in this context, animal, sorry, animal, the value of animal is that it is the main actor in this context, the one that's making the decision. Then, if we look at the street, the key of street is that it's an object, it's a location, it's something to be crossed. Value is the information about it being a path or an obstacle in this context. So we can see what key and value essentially means in relation to any specific word. Key is information about that word, and value is going to be the some more extra information about that word in this specific context, in this sentence that we are looking at. Tired is the key is that tired is essentially a state or a condition that affects living beings. And then value, it essentially means that tired is going to be related to fatigue or exhaustion. So something in this context or in this sentence is tired, and that is the value of tired. This key and value are essentially information that is encoded in the key and value matrix. Um, so when we compare the query of it, and query is a matrix of its own, with all the keys of all the words, we are going to take the query of this word and compare it to the keys of all these words. We will find out that it has a very strong alignment with animal's key because it relates to the subject of the sentence. Animal is the subject of the sentence. Only living beings can be tired, and animal is a living being in this context. That is why it refers to animal here. The grammar and structure of this specific sentence suggests that the word it is related to the subject who is a living creature. So that is why through this logical connection, we would be able to understand, or the machine would be able to understand, that it is related to animal here. It finds a very weak alignment with street because firstly, street is an inanimate object and it cannot be tired. The grammar makes it illogical. So to summarize, the query of each word is what is that word related to? The key is what is that word about, and the value is what useful information can be gathered about that in this context of about that word in this context. So in transformers, what we are trying to do is we are basically
So
using.
sorry, I have to interrupt you. Um, your voice is going on and off. Um,
Oh, okay.
would you like to try not using the earphone?
Okay. Let me do that.
Also, if you have any questions with what she just presented, please feel free to type in the chat or the Q&A.
Okay. I'm going to continue. Let me know if it gets stuck somewhere. Then I can.
Right now we're still having a problem with your voice.
Sure. Let me just recap quickly. Um, Basically, we are going to calculate three matrices: key, query, and value. For each of these words, we are going to check the query matrix of one word with the key matrix of all the remaining words to find out what's the relationship between that word and all the other words. And then we are going to essentially be able to understand what word is this word associated with. In this example, it shows that it is connected with the animal. Is this
Are you
something?
not using earphone right now?
I am not using your phone right now. Um,
No, we cannot really hear you. It's even worse.
okay.
Okay, so I can present for you for now. Okay, hold on 1 second. Okay, so to recap, we have three very important component in the transformer's attention mechanism. And the first one is the query. Query is what we're looking for, and it will look at all other words. Key is what is this word about? And then value is what is the useful information that should be gathered in the context of this sentence. Can you hear me now? Okay, good. All right. So let's get started with step number 3. In this step, we will randomly initialize weights matrix for query key and value using NumPy's random.rand function again, but this time instead of a vector, we'll initialize random numbers for the matrix. These weight matrices have a dimension of embedding dimension by head dimension. Head dimension equals to embedding dimension divided by number of heads. And head dimension is the dimension of each head. So in this example, we are working with only one single attention head. So head dimension will equal to embedding dimension. So that's saying that we'll have 3 matrix that has a size of 8 by 8. So now let's go ahead and implement this block. And once you're done, send a thumbs up. Okay, I see many of them. Okay, so the answer will be numpy.random.rand, embedding dimension and head dimension. In the paper, head dimension is different from embedding dimension because there is a multi-head structure. But here, since we're only working with one head, so both of them equal to 8. All right. And if you hit run, you will be able to see that all 3 matrices have a size of 8 by 8. All right, now let's start moving on. So once we have all the weights, WQ, WK, and WV, we will be able to generate the matrix Q, K, and V using a dot product between X and all these matrices. And we'll be using a function called np.dot function. So let's go ahead and implement step number 4. Okay, I see 2 thumbs up. Another one. Okay, plenty of more. Okay, so the answer will be just use an np.dot x with all the weights. So for example, the first one should be np.dot x and then wq. The same with the following 2 others. Okay. Let me turn these off. So you should be getting 3 metrics that are 3 by 8. And the reason why we get 3 by 8 is because X was 3 by 8 and W's are 8 by 8. So the dot product between them will be 3 by 8. Okay, so congratulations. Now you have Q, K, and V. We're gonna pause here to take some questions. It will take questions for 5 minutes. And if you want to use a stretch break or bathroom break, feel free to take that. So the collab is being updated and at the end will be complete. Yes. Thanks, Brian, for explaining. Yes, so right now we initial all the random numbers that we initialized will have no meanings right now because they're random. But after the training of the transformer or after the training of the neural network, they will be updated with all the back propagation. So then at the end, once we're done with the training, all these random numbers will have a certain meaning. We can get started in 1 or 2 minutes. Any other questions? The values seems too big to be used in neural nets. So the magic of neural net is we can have a very we have lots of parameters, right? All of the 8 by 8 matrices are uh are the parameters that will be trained. Oh, okay. Thanks, Shito. Yes, yes. So the numbers will be scaled into by softmax. So at the end, we'll have numbers between 0 and 1. Okay. All right, so let's get started again. So now we're at step number 5. I hope everyone is following so far. Step 5 calculates attention score. In this cell, we compute a raw attention scores by taking the dot products of Q and K. Remember, Q is 3 by 8 and K is also 3 by 8. So we need to transpose K so that they can take dot products. And then after that, we will use np dot function. For context, this step involves doing a dot products of the query vector of one word with the key vector of each other words. And so the resulting scores will tell us how each word is related to other words in that sentence, indicating a level of attention. So for example, you are amazing. Amazing's query will have dot product with the key of U and the key of R to see how amazing has attention to all the other words. So go ahead and implement step 5 and hit a thumbs up when you're done. All right, so this one looks good. I saw a lot of thumbs up. Okay. So the answer here is np.q and k.t. Once you hit run, you can see that because we have a 3 by 8 matrix of Q multiplied by an 8 by 3 matrix, which is K's transpose. So at the end, we have a 3 by 3 attention score matrix at the end. Right now, you see the numbers are quite big, 119. So we need to scale them. So that would be the next step. Okay, so we are here. We have finished matrix multiplication. The next step will be scale. In this step, we will explore the shape of K to understand that why we should scale using the value of dk. Dk is the dimension of the K vector, and in this case, it is 8. We want to scale the attention score by dividing them by square root of dk. The reason why we scale is we want to push the number smaller so that it gets to the middle of the softmax function. As you can see that if we have a very large number and we apply the softmax function, you are either at a number that is very close to 1 or a number that is very close to 0. And we don't really want that. We want to push the numbers into the middle to have more variance of what variance of the probability. And then another reason why we scale by square root of dk, because we want to bring the variance to 1. So it's normalization or standardization. Okay, so let's go ahead and implement step 6. Oops, step 6, yeah. And then let us know once you're done. Okay, I saw some thumbs up. So the first question mark here is how much is decay? And the answer is k's second dimension, right? So it should be k dot shape 1. In this example, we're setting the dimension of k, the dimension of wk the same as embedding dimension, so 8 by 8. But k is 3 by 8, so dk is 8. Okay, next we want to scale the score by mp dot square root of dk. Okay, so okay. So this is what you should get at the end. dk is 8. Scale detention score is 42, 50, 40. And shape of scale detention scores is 3 by 8, 3 by 3. Okay. All right, so we are here. We have finished the scale block. And then the next part is add attention mask. Mask is optional. See, there is an optional here. In the encoder part, mask is not needed. In the decoder part, we'll use the mask because we are trying to predict the next word, the next token, right? So we don't want the model to look into the future. Okay. So step 7, in this cell, we will create a 3 by 3 mask matrix where the lower triangle is 0, meaning that we don't mask them. And then the upper triangle will be minus infinite. For this case, we'll use mp.triu, triangular upper for quick generation. You can also just write a 3 by 3 matrix on your own. Okay, so go ahead and implement step 7 and send a thumbs up button if you are done. If you're not able to do it in just one line of code, it is also okay to use multiple lines. I see that there are not many thumbs up, so I'm just gonna give you the answer. Okay, some more. Okay, that's good. So if you just use mp.try, you get an array that you have a lower left triangle of ones, and then the upper ones are zeros. That was not what I want. I want the ones to be zero, and I want the zero to be minus infinite. So how do I do that in one line? To show that I have fancy skills. Um, then I will use a log function, right? Because in a log function, log 1 is 0, and then log 0 is minus infinite. So I'm playing some tricks here, but you can do that with other ways too, as long as you have that triangle. So once you hit run, you have a mask that the lower left are zeros and the upper right are minus infinite. Your diagonal should be zeros as well, because each word should be able to see itself. It is just not able to see the future. So for example, in the sentence "you are amazing," if you are standing at you can see itself, but you cannot see "are" and cannot see "amazing." Okay. And then we add scaled scores and math together. So then now in the mask attention scores, you can see that the upper right triangle are minus infinite. So 4, 6, 7. All right, so we are here. We finished the mask. Now let me move on to Shefali to finish the last two steps.
Okay, hi everyone. Sorry, I was on mute. Does anybody mind sharing the Colab notebook? I think you have
Oh,
the
sure.
latest version, so thank you. All right, I hope I'm audible to everyone. If you have any issues with my voice, just put on chat. But yeah,
It's
so
good.
we are done with step 7. Okay, thanks. We're done with step 7. So we have the attention output, but it's masked right now. The next step is softmax. What you would see in your output right now is that you would see a bunch of numbers, but you don't really know what they signify because you don't know which word to predict next. When we want the primary purpose of the transformer in this context, when you're using the paper, is to tell you what is going to be the next token in your sequence. And to understand that, you need to have some kind of way to rank the output, which gives you an answer where you can say that, okay, the highest number is going to be my next token that will be predicted as output of my transformer. If you've done multi-class prediction before, you would be familiar with something known as softmax. We briefly covered softmax in the previous step, but what it really is just a function which takes the number as an input for each token, and then it scales it such as the output is in a scale between 0 to 1. What that really does, or like an intuitive way to think about it, is that if a word has a really high compatibility score with, say, two other words, softmax function, the way it is written, is going to make these differences even more pronounced. So if we scroll down, okay, so this is excerpt from a very popular 3 Blue 1 Brown blog, and you can see how the output on the left-hand side was simply numbers, but we're not able to meaningfully interpret this to say which should be the next token in the sequence. But when you apply softmax, you can get as an output a probability, and it tells you which token has the highest or which token has the highest probability assigned to be predicted. Which is why in the last layer you see softmax being applied, and that's what we've done in step number 7. So go ahead and look at the code block for step number 7. Yeah. So go ahead and look at step number 8. Look at the code block for step number 8, and you can fill in the answer over there. As a reminder, the function is given above. It's the exponential divided by the sum of exponential of the input. If you're able to fill in the function, just give me a thumbs up. Just as a reminder, this is the function from NumPy that we can use to generate exponential. Okay, I see some trailing thumbs up. So I'm going to take that to mean that you're able to at least figure out how to use the exponential function, but this is the final answer. If we were always going to predict the top token, we wouldn't need softmax. So how would you know that you're predicting the top token? You need softmax to tell you which one is the top token, so to speak. When you have all of the scores at the end, to meaningfully understand which one has the highest probability of being generated, yeah, so the biggest score is something that softmax helps you understand. It doesn't give you any new probability. It's a simple transformation, which is like putting all your numbers between that scale of 0 to 1 so that you can understand which one has the highest probability versus the lowest. So it emphasizes that high and low that we see in the scores that we've generated. Um, okay, so now we're at step 9, but yeah, so we're at step 9 now, which is the final step, and we're gonna sorry, can you scroll up, Jason? I think I skipped past one. Yes. Okay. All right. So I wanted to emphasize this matrix because now that we've applied softmax, I mean, the first thing I want you to notice is how when we had used masking, we had set the upper diagonal to infinity. And when you apply softmax, it all turns to 0, which is what we want. We don't want the model to see the subsequent tokens. We only wanted to focus on the previous tokens. Let's interpret this a little bit. What this is basically saying is that the first row, which is u versus u, is paying 100% attention to itself and zero attention to the next token r and amazing, which is what we want. Um, when the model looks at r, it's saying that there's some kind of relationship between r and u, very very small, but the r is more strongly related with itself, which makes sense. And then the same thing is happening here at amazing as well. Amazing is more strongly related to r, and then a little bit to itself, and then a little bit to you as well. I do want to emphasize here that remember we initialized with random numbers. We didn't use word embeddings, which are specifically generated using an embedding model like BERT or word to vector or Glove. So I would recommend if you're trying to find actual um, if you're trying to find the actual embeddings to train, I would recommend using an embedding model. But right now, these are random numbers. So this attention score doesn't have as significant a meaning. If we wanted to see a more significant meaning, or if we had used actual word embeddings and train, we might see a higher self-attention between you, but we would also see more moderate attention between R and amazing, which would basically represent some kind of syntactic or semantic relationship um, between the words and the tokens that we've used. But if you scroll down and come to step number 9, okay. So now we're at the final step. We have the attention weights, and we now need to put it back somehow into our input matrix. If you remember, we had initialized a value matrix as well, which is the information that is going to be weighed by the attention scores that we've just computed. It's actually a simple calculation. It's attention and value matrix dot product. The code block is, yeah, it's visible on the screen. So go ahead and put in the code for step number 9, and that will be your final code to compute the attention output. Just as a reminder, this is the dot function that we use in NumPy to calculate dot product between two matrices. Thanks, Jason. If you are able to get to the final attention output successfully, please send a thumbs up. I'm already seeing a few of them on screen, but it'll be great if everyone can just react. Great. Okay, perfect. So when we run this code, we will see that now we're back to the original input side that we put in, because now our information has been weighed by the attention score and our matrix is of the size 3 by 8. You can see the output of the attention, the final attention output down below. This would feed into the subsequent layers, and I'll talk about parallelization in a second. But right now, we've just gone through the base calculation for the first layer for a randomly initialized set of embeddings, which are also 8-dimensional. In reality, when you're running or when you're coding any kind of neural network transformer, you would have embeddings which are more meaningfully generated using a model, like I said. It would be a much higher dimension in size. You would also likely to have multiple heads. So I'm going to come to that concept in just a second. And you would also train the weight matrices. We right now just computed the attention score, but you would use back propagation to compute the weight matrices so that your attention is actually more meaningful. So you're actually getting a meaningful answer at the end output. All right, so that's it. Let me just quickly go over the summary before I switch to the slides. So we started with the sentence, "You are amazing." We use a random numbers of size 8 dimension to generate vector embeddings or word representations. We started with a 3 by 8 matrix, which had positional encoding as well. We went through the attention mechanism. We covered query, key, value matrix. We initialized the weight matrix for them, and we calculated attention score. We also scaled them. We applied masking so that the model could not peek at future tokens, so to speak. And then we used softmax so we can get a meaningful probability to understand what will be which token is the most likely to be predicted next. And then finally, we put all of that together to add in our attention weights to the value matrix. And yeah, that's the output of one layer for one head. But let's look at what really happens in reality. So I'm going to go back to the slides for this. Jason, I can share the slides. Thanks. Okay. Okay. Let's go to the last slide we were on. Okay, so we just went through the entire notebook for calculating self-attention mechanism. I hope this was helpful for everyone. But right now, like I mentioned, we've worked with a single attention head. If you look at the original paper and you look at the model, you multiple attention heads, clarified by this NX. And you also have this happening in parallel. So I'm just going to show you a clip to show you how that happens. But before I get to that, let's look at this diagram over here. We've seen the one on the left hand side before, where if you look at one head, you see that for the word it has different attention given to different components of the sentence. On the right hand side, let's look at that visualization a bit more clearly. You can see that if you look at the word it has several colored lines which are connecting to different words. Some heads, let's say the pink lines, are more strongly attending to animal, understanding what it refers to. Other heads, like the green lines, are connecting to walls, trying to understand the grammatical structure of the sentence. And some other lines, like the blue and the purple ones, maintain connection to other words which are also contextual to the sequence. The point I want to make over here is that different heads can show you different kind of semantic and syntactic relationships between the context. Some are focusing on which pronoun to be used, other are tracking grammatical dependencies, and some are just maintaining broader contextual awareness. And that is basically the power of multi-headed attention. It's not just doing the same analysis multiple times, but it's performing specialized analysis in parallel, which each kind of contribute uniquely to the final representation. Um, and then what I wanted to finally also show for multi-headed attention was this slide. This is an excerpt from Attention is All You Need paper. As you can see, there are multiple heads that work in parallel, but let's go over this clip from a very famous blog by 3 Blue 1 Brown. If you haven't heard of it, I would highly recommend checking it out. They have some beautiful visualizations of attention and LLM. But what I wanted to show you is how these computations for attention happen in parallel, as you can see on screen over here. And then you have multiple layers stacked against each other. So your output is not only being sequentially processed, parts of it is also being processed in parallel. And then your input feeds in through multiple layers. So we haven't done multi-layer perceptron yet, which is another
Shafali,
way of saying feed forward as well.
Shafali, interrupt you
Yeah.
very quick. Can you hit slideshow to make it bigger?
Oh, can you not see clearly? Oh,
Slideshow, upper, yeah, this one too. Yeah,
can you see now?
this is. Mm-hmm.
Okay. Sorry. So let me just quickly go over that again. So I wanted to show you how the computations are happening in parallel. And additionally, you have multiple layers stacked against each other. So you not only have sequential computation happening, but you have parallel computation happening in a transformer, which is why the beauty of it is also not just that it uses self-attention to increase and to understand long range dependencies and increase contextualization. It can also be performed in parallel, which is why you might have heard that we use GPU, and it's so powerful because it can be done in a smaller amount of time, even though it uses a lot of resources. So this is what you can kind of imagine. This computation happens over many repetitions, as many as needed, based on the transformer you're thinking. And then the final output you would hope is the final column in the last matrix would have the scores, which will give you the probability of the next word being predicted. So the end output that we see from the entire process of the transformer after doing feed forward, attention, encoder, decoder, everything is going to be the final word that should be predicted, which kind of looks like this. Okay, so let me move on to the next slide. All right. I also want to emphasize that we did focus a lot on the self-attention mechanism over here, but that's one part. Of course, that's one of the most, the biggest part of transformer architecture. But there are other layers that facilitate which facilitate a transformer. One, you have the encoder box, which is the green box, which has two main components. It has self-attention, what we've been studying so far, where each word looks at other words in the input, and it has the feed forward, which processes the attention outputs even further. And then you also have decoder, which has, again, three components. It has self-attention, encoder, decoder attention, and then the feed-forward layer. You can think of it this way, in very simple words. The encoder kind of deeply understands the input, like comprehending the sentence in English, so to speak. And then the decoder uses that understanding to generate output, like, for example, reconstructing that sentence in English to French. The other thing I want to emphasize is when someone did ask about masking initially in this chat as well. So in encoder, when you're looking at, this is the encoder layer and this is the decoder layer. So in encoder, when you're looking at the attention, you will see that there's no masking because encoder is again understanding the entire sequence. And then you use masking in decoder so that you can predict without the model cheating or looking at the future tokens. But yeah, putting it all together, this is what your transformer looks like. We did focus heavily on the self-attention part of it, and the encoding and embedding part of it, but we haven't gone into depth for feed-forward layers, encoder, decoder, add norm, and residual connections, all very important components of the transformer. Um, I'm gonna go to the last slide now, which is the summary and conclusion. Okay. So just to recap, we started with the history of transformers and the importance of understanding them in depth. We did go over the key components at a very high level, at an abstract level, to understand what the model really looks like. Then we dive deep into getting our hands dirty and going through the Colab notebook to understand how do you actually compute self-attention score. We did that with a random initialization of word embeddings. which were 8-dimensional. And just again to reiterate, in real life, you would use a word embedding model, which will give you a much higher dimension of embedding. And then once we went through the step-by-step guide to developing the self-attention mechanism, we came back and we kind of again had a very high-level view to understand how does multi-level, multi-headed attention and encoder-decoder blocks work. And then lastly, I would also want to highlight that we, throughout the presentation, you would see that we've cited some sources from different blogs. I would recommend going through all of those blogs as well. Really a bunch of information and really beautiful visualizations that you can find. But yeah, that's it. Thank you so much for joining us today. Anything to add, Chusen, Sheetal?
I guess you guys can go ahead and train these models now and make these numbers meaningful.
All right. If there's any, we have like 5 minutes left, so we got done early. Yeah, yes. But if there's any questions, feel free to put it on chat. Um, and I see a lot of claps, so thank you. I see a question on what would be a good example of intro and intermediate projects that I can implement with making my own transformer. Okay, I think I will just take one quick shot. Okay, thanks. So I think for this one, I think coding your own transformer from scratch would be a big achievement as well if you can do it. Not just the attention output, but all of the layers. The second thing I want to highlight is training a transformer is a very resource intensive task. And when I say resource intensive, I mean like millions of dollars of investment. So you can use some pre-trained transformers which are available. Open source ones can be found on Hugging Face. That's the most popular one. But you can also use other APIs. You can use pre-trained GPT transformer, for example, or Claude, or any of these other models that exist, and incorporate it into some of the use case, like create your own chatbot or something like that. But Chusin, Sheetal, any comments?
I think there are lots of use cases of transformers. You could try with like machine translation. That is one of the examples. I think the projects that you can probably consider are the ones that you'll find data easily for. So just go on Kaggle, look for the data that you want to implement with. There are vision projects with transformers. There are NLP projects. NLP probably, I think you should be able to find a lot of good data sets to work with.
Pre-trained ones are available on Hugging Face. Let me share the link. So the Hugging Face has the largest repository of open source pre-trained transformers, meaning you don't have to pay for it. Of course, you have to still pay for the computation if you're fine-tuning it or using it for other use cases. Yeah, Colab and Kaggle also has a lot of uses. And then if you can pay a little bit for the tokens and you want to see how GPT and other models work, you can use their API. All right. I think that's it. If you're talking about signal processing, I'm not a subject matter expert in that. I think there have been some papers that have used multimodal transformers for signal processing, but again, more information can be found on Google Scholar and other research publications.
No, I think they meant signal as language. So you can use it for
Uh,
vision as well. And it has been used in other multimodal applications, as Shifali said.
a very good object detection algorithm is RTTTR, um, which you can see for application of transformers.
All right, with just 2 minutes, a little less than 2 minutes left, if you all want to do your final questions, we also encourage you all, if you have more questions, please hop over to Discord, and you have a channel there called Workshops and Tutorials, and you're welcome to ask any questions and engage with the speakers there. But it looks like you all got most of your questions answered. So thank you, everybody, for joining us today. Thank you, speakers, for your time and energy put into this and for being a part of the PyData community. Attendees, I encourage you, we will be having a keynote from Peter Wang starting in just a couple minutes. If you'd like to join that, you'll find the link in the schedule. Thank you, everybody.
Thank you.